Let me welcome you all to the Trueblood Award Lecture. The Trueblood Award was established in 2001 in memory of Professor Kenneth N. Trueblood, who was at UCLA from 1949 to 1998. He was a major force in the early use of computers and the development of crystallographic computer programs. He applied these programs to the examination of chemical and molecular details of many structures at the frontiers of research. His contribution to famous work on vitamin B12 is one of the examples. Professor Trueblood was a leader in the development of techniques for analysis of anisotropic motion and was also a superb teacher and lucid author. As a matter of fact, as a graduate student, I needed the TLS routines he put into a program called ORFLs to do a very difficult structure, large small molecule structure that I had to finish up my thesis. So I learned a lot about his coding techniques then. The Trueblood Award recognizes exceptional achievement in computation or chemical crystallography. Previous winners are Dick Marsh, Angelo Gavazetti, Tone Spack, and Tom Terwilliger. This year, the award will be given to both Bob Van Dreele and H.Toby for their work on GSAS-II, a general-purpose program for crystallographic analysis. It is unusual to have the award be given to two people as the fifth time. It hasn't been done yet. So I thought it might actually be interesting to have Brian and Bob introduce each other since they've been working together for so long.
I wanted to point out two things that Bob has done, one of which is a small thing, making time-of-flight neutron diffraction possible. A second thing is that Bob has shown that from powder diffraction it is not just possible to refine protein structures, but even to solve structures of previously unknown proteins. Bob started his career at Cornell, where, as I recall, he was a member of, lacking on the name, but a non-Greek fraternity, where it turns out, I found out just recently, he was a fraternity brother of my future brother-in-law. And he was eventually kicked out of Cornell with a master's and then a PhD. Went on to spend 15 years approximately as a faculty member in Arizona. Retired from that. Arizona State, okay. Retired from that, went to Los Alamos. Went from Los Alamos to Argonne National Labs, where he is at present. And Bob will be telling us, let's switch to the talk here.
This is from 1972 to GSAS-II, and so I'm going to actually give you a little bit of a history lesson in computing, at least from my perspective. Let's see now if this works. So where did all this start? Well, it began when Tony Cheatham walked into my workspace at Oxford. We were both postdocs at the same time in 1972. And he walked in and said, "Bob, how would you like to do a neutron and powder diffraction experiment?" And I said, "Sure, why not?" So the place that we did it was here, the Pluto reactor at Harwell. And this is the sort of characteristics with respect to the neutron flux. And the Panda diffractometer was an outline here, I believe was down in this pit. I'm not absolutely positive. After all, it was 40-odd years ago. It may, in fact, actually been somewhere back around there. But this is where I remember it. And so what we did was we said, okay, let's back the monochromator around to the highest angle to give the best resolution. And the kind of thing that we were going to look at, oh, by the way, the scan rate was 50 minutes per degree. And so that means that the experiments were 3 days apiece. And so oh, by the way, just as an aside about computing, is that typical programs at the time worked like this. You had a deck of cards, you had some sort of a program, it ran for a while, and it spat out a deck of cards, which you then take and put back into the beginning of the program. And there may have been some information on a magnetic tape or a paper tape even, and it would spit it out as a printout and maybe write stuff to that precious commodity, a disk file. All batch processing, no interaction with the user. You simply start the thing off and come back the next day, because that's how long it took to run these things. Okay, the program, I'll get to what we did in a minute. The program was this thing that Hugo wrote in Fortran after he had written the thing in Algol. And this is a copy of the program guide from Alan Hewitt that detailed how you ran the thing. And what I did to it is to make it do larger structures, because as it turns out, the structures Tony and I were interested in were simply too big for the machine we're running it on. And I also tried to put in X-ray powder diffraction, but it didn't work because it didn't know what the peak shapes were. So the next question is, what did it run on? Well, it ran on this. This is the thing that would fill a room almost as big as this one. And here is its characteristics. It's around 800 kilobytes. The memory, I believe, was magnetic core. And by the way, this is a little picture of a magnetic core, which is 8 bits by 8 bits. So that's 8 bytes. The chip on the top is an 8 gigabyte chip, a modern one. That's 9 orders of magnitude. That's Moore's law, right there. And that's what has revolutionized crystallographic computing more than anything else, is this scale. Right. So here's what we were looking at. These things were titanium niobium oxide, so-called block structures, which were all the rage in the 70s, it turns out. And these things were sort of blocks of niobium octahedra, corner shared, and then somewhere along the edges, some of them were edge shared, and odd bits of things happened when at the intersections of the blocks. These are very pretty structures in electron microscopy, and that's why they were sort of all the rage, because you could almost see the atoms in electron microscopy images at the time. These things are big. We're talking about 11 by 20 angstroms. This one axis is short, which was a bit of a cheat. And the numbers of reflections was large, 600 in this case and 800 in that case. And oh, by the way, this is what I presented at an ACA meeting in 1974 at Berkeley. There may be a few people in the audience who might remember that talk, but that was from quite a long time ago. And this was published in the Proceedings of the Royal Society back in 1974. And by the way, these two structures were in fact some of the largest structures done by powder diffraction for quite a long time, until people started doing zeolites and things of that sort. Although, as I said, they're a bit of a cheat because one axis is short, so they're really sort of just two-dimensional structures. Nonetheless, there they are. I should note that the drawings and the powder patterns were in fact hand-drawn on vellum because the computer graphics was not up to the task of doing that kind of thing. I had to trace the patterns in order to get these figures. Okay, now a little bit about Hugo Rietveld's computer program, which, by the way, I think were called Pref and Prof because there was 2 steps to the process. One which was to find out where the reflections actually contributed to the profile and then submit that stuff to the least squares program, which would actually do the refinement. This was, Alan Hewitt got a copy. He added anisotropic temperature factors. I got a copy from him and modified it to do much larger structures, the 2 that I showed you, and add X-rays which didn't work. I then handed it off when I got back from Oxford the first time in about 1974 to Ray Young at Georgia Tech, and he and his students got the X-ray thing to work. He simply explored all the possibilities for peak shapes and discovered that pseudovoids and things like that seemed to work pretty well. They rewrote the program so it would actually run on an IBM PC. And Ray Young, Tony Cheatham, and I then went on tour of Brazil and Argentina and Poland to teach people how to do Rietveld refinements. We called it the Rietveld Refinement Roadshow. And and it's very effective because there's lots of people who still remember those courses. Anyway, this program then is the ancestor of things like FullProf and LPHM in Australia. The Philips instrument package has it built into it, or it used to anyway, and there may be some other descendants. Well, I went back to Rutherford in 1982 on a sabbatical leave, and as Brian mentioned, I explored the problem of how to get the read-file refinement to work with neutron time of flight data. So I had to discover what the peak shape should be, how the peak shape varied with d-spacing or time of flight, and I used this code here that I was familiar with to implement it. That program then became the basis of the program that was used at IPNS at Argonne for a very long time. So that's actually the history of these kind of things. Right, okay. When I got back from Rutherford the second time in 1981 or so, I knew that Phoenix, Arizona was simply too hot a place to be in the summertime. So we spent summers at Los Alamos, and Los Alamos paid me for my time for 3 months, which, by the way, Arizona State did not pay me for those 3 months. So early on in that process, the group leader, Richard Silver, came to Alan Larson and myself and said, Alan, you're going to be responsible for the single crystal analysis codes. And he looked at me and he said, and Bob, you're going to be responsible for the neutron powder diffraction data analysis programs. And we looked at each other and said, why do this twice? So we said, all right, let's write one code that did both at the same time. And that's then how GSAS got put together. It is written on a VAX. It uses the so-called ISAM file structure, which allows us to access individual records in the control file, basically, at random, without knowing their position in the file. All you had to do is know a key, and then you could find the rest of the record. Very much like a modern dictionary in Python, oddly enough. Excuse me. It had to deal with multiple data sets because that's how neutron time of flight data came out. You had multiple banks on a powder diffractometer, and the images that you got from the single crystal were simple multiple settings of the crystals. So you had a couple dozen crystal settings. And this thing was so complicated because of the interaction between the parameters that we knew that a user would have no chance whatsoever of following the classical manual constructing individual records for this particular thing and feeding it in as a deck of cards and hope that it would run successfully. There was just no way that could happen. So we wrote this thing called ExpEdit. And some of you may be familiar with this page, which is the menu-driven single character keystrokes to get at all of the items in the experiment file and allow you to change them. People either loved that thing or hated it. And it allowed you to type ahead so you could actually go in about 15 or 20 steps, change a parameter, and back all the way out on one line of typing. This was state of the art in 1980 something or other, 85, which is when it came out. Brian then said, well, this is not good for beginners. So he wrote ExpGUI, which is a graphical user interface to do much of what this does. Didn't cover everything, but it certainly covered all the essentials. And it had all the usual sorts of stuff, pull downs and buttons and fill in the blanks and all that kind of thing that you expect to see in a GUI. GSAS then went through an evolution over the next 20 years almost, in which the first thing to do was to get it to run on something other than the VAX, and the folks somewhere, I forget where, gave me a Silicon Graphics little purple box machine. And I was then able to port it to IRIX, which was the operating system, a lot like Linux, and then to a PC, and then finally someone else, I think Alan, ported it to OS 10, or maybe Brian ported it to OS 10. Excuse me. And it also included, during this time, well, I added constant wavelength neutrons and X-ray analysis to it, and profile functions were being developed by people in the community. And so as these were developed, I implemented them in the code so then they would be available to me and also available to anybody else who wanted to use them. And so that's the main thing that went on, one of the main things that went on. The other thing is that I said I was responsible for a high-intensity powder diffractometer at Los Alamos, and I said this thing is ideal for doing texture measurements. How do you do it? So I implemented spherical harmonics analysis in a Rietveld refinement to analyze texture. And also got the crazy idea of saying, well, what would happen if you took a powder pattern of a protein? And the shock was that the lines were sharp, sharper than the standards produced by NIST. And so I said, I had to do something with that data. So I put into the Rietveld refinement code the capability of analyzing protein structures and managed to refine a couple, solve one, and also demonstrated other aspects of protein crystallography for powder diffraction. GSAS is rather easily scripted, mostly because of that keystroke menu options. It's documented in something called the GSAS manual, which has a Los Alamos laboratory report number, and that's the only publication. It's gone through 7 editions, in which I took a picture of all 7 editions that I had on hand. This is the 1985 version, and this is the 2004 version. This one is about half as thick as that one. It's been cited often, and it's still being cited often. But the problem is that it had reached design limits. You simply couldn't expand it beyond 99 histograms, 99 powder patterns. The interfaces were dated, difficult to use, and clearly there was a steep learning curve for both of them, particularly for the first one. And it lacked all the kinds of tools that you need for solving structures. So we had to have a new tool, which we call GSAS-II, and the goals for GSAS-II are as follows, and this is a whole lot of stuff. But the key point is that we want to cover the data analysis from beginning to end. And we wanted to do the same thing that the old GSAS did, which is X-rays and neutrons, and we wanted to make it more general, which is to include small angle scattering and reflectometry, and also generate pair distribution functions. And basically, it also now allows one to do combined analysis like the old GSAS, but also sequential analysis, where you do the same calculation over a whole series of data sets. And this was not to be limited by the sizes of data structures. Basically, there's no limits on the numbers of patterns and phases and whatnot. I used a bit of the old code, and it was needed to be in a modern, easily accessible computer language. No exotic things. And had to have a modern graphical interface. Graphics everywhere. My feeling is if you have a table of numbers, you should be able to draw a picture for it, no matter what it is. And it had to be open source. That means everybody gets the source code as when they download the package. Because that way you can see what I did, and you could also modify it yourself. And it should work on all the platforms, and the code development had to be agile, not one of these things where you blocked everything out and made header files and then worked out in the end finally. Somebody asked me a long time ago, said, oh, how come you didn't use a serious computer language like C++? And my comment is, I'd still be writing header files 10 years later and have no code to show for the effort. The language then is Python with the libraries that gives you speed, graphics, the GUI, and the graphics for drawing molecular structures. It started in 2008. The first usable version was 2012. The current version number, because of updates, is 4,060 something or other. So it tells you how often we update it, sometimes more than once a day. Now it's somewhere on the other side of 100,000 lines of code. 75% of that code is for the GUI. Roughly 5% for reading files and that sort of thing, 15% for the mathematics. That tells you something about the balance of the emphasis on when you write one of these programs. The mathematics is easy. It's the GUI that's the hard work. And 5% for the graphics. All that fancy graphics is in 5% of the code. Okay, a little bit about event. How am I doing on time? Okay, fine. A little bit about event loop systems, because that's how modern computer programs actually work. First of all, here you are doing something with a mouse, looking at the screen, and I think what it is, I've set it up so that you're looking at a drawing of a crystal structure, and you want to actually just rotate the structure around so you can actually see the other side of it. And so you're talking to GSAS-II, and it's talking to a file that's on a disk. Well, what really happens? There we go. What really happens, you move the mouse through the operating system back end, that gets converted into an event. And it goes around this event loop, surveying all the possible things that can handle that event. And it finds this one, on mouse move, which says because you moved the mouse, that's the event that's generated. This little routine, which is something I had to write, which then does two things. First of all, is that in the mathematics, it rotates the molecule. It finds the increment to apply to the quaternion that's used to describe the orientation of the molecule, and increments that. Then that updates the orientation in the project file, strictly speaking is on the tree. And then the second step is to tell the code that renders the molecule, okay, redraw it. So then it goes back through the back end with all the commands for drawing it, and you then see the thing rotate. That's how these things actually work. Why Python? Well, this plot I found, these are friendly people, shall we say, in our community, and they sort of, their estimation is that Python is really fast at developing something new because its programmer productivity is high, but it's slow. And yes, it would be very, very slow if you wrote Python as if it was Fortran, full of loops and all that kind of thing. Terribly, terribly slow, because Python is an interpreted language. Every line has to be looked at by when you do the calculations. But there's a way around this, and that is to add the NumPy package, which is an array processing routine. And so if you reorganize the code to get rid of all the loops and you simply do them as arrays, then the calculation is much, much, much faster and is in fact competitive with Fortran and C. Right. Now, here's a little snippet of code. And then the code is the charge flipping algorithm inside GSAS-II. And this is the actual lines of code from there to there. So it's on what, 13 lines of code to do charge flipping. And you can see exactly what each step in the process is between the initial Fourier transform, the charge flipping, the reverse transform, extraction of the phases, and you get a new set of phases applied to the structure factors. And you go back and do it again. And this stuff down here is housekeeping, so you can keep track of what the residual is. That's it. Easily seen, easily read. And my second example, which I'm actually going to skip or go through extremely fast, but basically an omit map can be calculated inside GSAS-II in 65 lines of code. as opposed to some 9,000 lines of Fortran and C that's in the CCP4 package. So finally, GSAS-II, now some graphics from GSAS-II, and these are graphics that Brian solicited from GSAS-II users because this is going to be on the cover of the next issue of Reflections. I believe it's the next issue. And the thing that impressed us is how many of these figures, in fact, most of them, have to do with multiple data sets showing phase transitions in some cases, other kinds of changes in the structure as you raised or lowered the temperature. All of that sort of stuff is all part of, I mean, look at this thing right here. But also featured on here are things like contouring maps, magnetic structures, image processing. This is one I added later for highly tilted detectors. And with that, I thank you. And next up is going to be Brian Toby. I would say one or two things. The key point is Brian Toby is my boss, so he gets the last word.
Okay. Thank you very much, Bob. Okay, so I'm going to take this talk a little bit in a different direction. That's the talk title, but there's a couple things that I really would like to do. I'd like to start by mentioning that my career in science has had a lot of ups and downs, and I really think it's important to communicate that, particularly for some of the younger people in the audience. I'm proud of the work that I've done. I feel, and this award means more to me than I can possibly say. But I'd like to, in this talk, I'll talk about some of the people who've really, I can't talk about all the people I want to thank, but I do want to thank Winnie for the nomination. I want to acknowledge a few people who've really helped raise my career, and very few of them are in the room, but that's all about paying it forward rather than paying back. And I will then switch to talking about some crystallography and introducing the concepts of subgroups and supergroups and how that actually relates to the Trueblood Award. And then finally, a few things relating that to work we're doing in GSAS. So let me start by mentioning my parents. Now, I'll say that some of the aspects of my career, or at least what I'll call the process, were not necessarily so good. I wasn't raised as a very confident person, perhaps a little better with self-reliance and resilience. But the one thing that my parents really did bring with me was a love for science and learning. And I think also I acquired some of my father's writing skills. But I also want to let you folks know that it's my mother who introduced me to computing. When as I think probably about a fairly young teenager, she took over the computing from my father's research group and brought me to the computing center that back then at Rutgers there was a computer. I also would like to put in a word here for Canada. My mother came to Canada as a refugee. At that time, the United States did not have terribly open immigration conditions, and I probably would not be alive if it weren't for the fact that Canada admitted my mother's family. My father, who grew up in London, met my mother at McGill University and moved to the United States shortly before I was born. I went to Rutgers as an undergraduate and actually majored in the same department where my parents worked. That's a long talk, we won't go to there. But I very definitely remember shortly before the end of my first year, I was looking for a research job. And Joe Potenza, who you see over there, was one of the professors I spoke to. And I remember very distinctly Joe saying to me, if you choose to work in this group, not whether if I will hire you or not. And that was a wonderful experience. Joe was a Lipscomb-trained crystallographer, and I guess it was easy for him to say that because he was using money from Harvey Sugar to pay me. Harvey and Joe ran a group together, and it was a place where research was fun and collaboration was so expected it was just it just didn't get mentioned. While there, I was able to co-author 8 papers, which included 9 faculty members in total as collaborators. It was a great place to work. Probably the less I say about my graduate school experiences, the better. And then my first job at Union Carbide, rest in pieces. We won't talk about either. But Union Carbide did send me to the National Synchrotron Light Source when it was just getting started, where I did some work with Dave Cox. He introduced me to Rietveld, got me started working on a different descendant code than the one Bob talked about, but also from the ancestry of Alan Hewitt. I got a chance to see synchrotron and neutron diffraction, and I'll just say, unlike my graduate work, I really discovered that research, again, was fun. And I thank Dave tremendously for that. Takeshi Agami rescued me from Union Carbide. We worked together on developing PDF analysis for crystalline material, and I was able there to create the first small box PDF fitting program. The next stop in my career, and I really need to thank, I haven't put their names on it, but let's see if I can point this way. Mike Rowe and the late lamented Jack Rush, who saw potential in me that I didn't know I had, and asked me to lead the crystallography group, which consisted of Ted Prince. It's a rather strange thing when you're put into, when you're asked to supervise one of the world's leading crystallographers. Tony Santoro, who was actually at that time is about within a month of my father's age. That was also pretty daunting. And I got to learn a tremendous amount from them, but I learned way more from Judy Stalick, and I owe tremendous gratitude to Judy. One other place where I really have tremendous gratitude to is my family. My wife, Diane Toby, who's a PhD psychologist, and I can't stop pointing out that there are a number of us in crystallography who have acquired in this process partners in mental health. We can take that where you want, but I will say that that my family is really where my strength comes from, and I am very grateful to have had the chance to raise 2 sons, Jason and Josh, and about a little less than 10 years ago, we acquired the glue that keeps our family together. That's Rocky. And the last person I really would like to mention in terms of the people who have helped build my career is this guy. This is the crystallographer who I've learned the most from. Around the time when email transitioned from ARPANET to the internet, I started asking Bob questions, and he's been answering them ever since. He gave me the source code to GSAS, and I have returned the favor by porting it to Linux and eventually the Mac. And in 2005, we got the chance to start working together. And Bob, thank you very much. It's been a pleasure to work with you. All right, so transitioning a little bit. It's also rather daunting to get an award like this that has the kind of heritage. The first award winner for the Trueblood Award was Dick Marsh. Here's Dick with the person who brought him to Caltech, Linus Pauling. And I did get the chance to TA for Dick Marsh, and I did get the chance to actually design an undergrad lab experiment that was done in his lab. And interacting with Dick was one of the few high points of my career at Caltech. But Dick made a career out of correcting the literature and it was very, very important to him that crystal structures be the resource, the correct resource that we are, to the level of that definition that I put up there, and I've heard the verb to marsh used many times. But I want to point out that marshing, and actually I also included over here a list of some of his last few papers. He published tremendously, looking for things in the literature that could be done better. And but I want to point out that Dick was specifically looking for where there is a higher symmetry space group that was missed in the initial study. And that brings me to the concept of subgroups and supergroups. As crystallographers, we tend to think of space groups as these entities, okay? This is CC, actually it's AA, but by accident, but anyway. And that's what we need to know about the symmetry of the that space group. What we don't often think about is that space groups are really in families. And I will bet that a lot of people don't bother looking at that section of the international table, which tells us how space groups are interrelated. And frankly, for this, volume A is just simply not adequate. It doesn't tell you how to do the transformations, and it gives you no feeling for the families that are created by of the interrelationship of space groups. So there you see CC, and you see how it's interrelated to one of Dick's favorites, which is correct space groups, which is C2 on C. And that family nature is the concept behind subgroups and supergroups. So armed with that concept of subgroups and supergroups, we can go back to visiting marshing and realize that marshing is the process of finding the proper supergroup. And I'd like to introduce a new term to you, which I'm going to call anti-marshing. Anti-marshing is when you find that the correct structure is in a subgroup. And why is that important? Well, if the symmetry is too low, then you're going to have real artifacts in your fit. But if the symmetry that you report is actually too high, you're missing the interesting bits. We're very interested, for example, in things that are not centrosymmetric because they're optically active or they're magnetically interesting or things like that, or they're thermoelectrically important. So it's important to get it right. And the best practice when we're doing crystallography is that we should be testing, is there higher symmetry? And we should be testing for lower symmetry. And unfortunately, that's not so easy. Now, volume A has an auxiliary volume, volume A1, which makes this process easier. Volume A1 gives us the transformation and origin change that's needed to transform from one space group to another, but it's still no fun. However, in the world capital of symmetry is Bilbao, and those folks have created a website that does everything that you just about would want to do with symmetry. Problem is that it's still no fun to use because you've got to take whatever you've got and cut and paste it onto web pages if you want to do anything. But I still recommend this highly. And in GSAS-II, we have adapted by adding access to Bilbao. And so this is work that Bob did, but as a good supervisor, I'll take credit for it because I suggested it to him. You can take a lattice and your units and your coordinates, and you can find all the subgroups, and here's what it generates, a list of the various subgroups that are related to what you've got. You can, and then you can transform the coordinates into those subgroups. More recently, we've started in the direction of marshing, as opposed to anti-marshing, and the first direction for that is to look for pseudosymmetry in the lattice. And is there a higher symmetry cell? I'd hoped to talk about more work that I had done here, but there's still stuff on my to-do list. So the next stop on this is to introduce the Bilbao's pseudo program, which will actually find likely supergroups using the coordinates. We need a tool to compare different refinements, so that's coming too. And I'll conclude by talking a little bit about that, well, for some of the younger scientists, my first ACA meeting was in 1988, and at that time I could never have believed that I'd be on this side of the awards podium. I know that I've had many ups and downs in my career. It's not been a nice linear path, and I hope, inshallah, in 30 years to still be here and see some of you folks in this spot here. I can't repay what I owe to those people that I've mentioned who've been really monumental in my career, but I can pay it forward. I'd also like to leave you that subgroups and supergroups are absolutely key to getting structures correct, and that we as a community need to make this process easier. And we're more or less on time.
So how long have you two been working together?
Let's see, we started working, well, it's a difficult thing because we were working together at a distance. When he was at Los Alamos and I was at various employers. But we really started collaborating in offices next door to each other, that sort of thing, in about 2005 or something. Somewhere around there.
So you want to elaborate? Do you want to say anything about your time at Caltech?
All right, very quickly. I chose the wrong field, and I'll be honest, I got some bad advice from Joe Potenza. He told me that there were no careers in crystallography, unless I wanted to do macromolecular crystallography, and then at that time, it was students per structure, not structures per student. And I didn't really want to do that, so I went into surface science, which was an absolutely horrible fit. And in retrospect, I think that I may have made a mistake by not quitting that group and going to work for Dick Marsh. I don't know still don't know whether that was the right thing or not to do, but at that point, going back, unwinding a year or 2 years of my graduate work just seemed like it was not possible, so.
Thank you.
You're welcome.
Any other questions?
Yes, Kate?
I just want to say thank you. My introduction to crystallography was showing up in Los Alamos and getting one of these manuals. I don't remember which color it was. But I also want to say you guys love, in particular for blog reference to tutorials. What you've done online is such a help to the community. As beeline scientists, introducing new users is so much easier for all of us. Thank you for that.
You're welcome.
Well, you're welcome. Thank you for the remark. The tutorials I wrote a lot of them, and it's a lot of hard work, especially a lot of hard work to keep them up to date as the code changes. But nonetheless, it's a good thing to do.
One of you that most recently for their decision to make GSAS-II open source. I learned more from getting to GSAS-II than open source.
Okay, first question, just to repeat from Kate, was thank you. Second one was not really a question either, but it's great that it's open source. I have a problem personally with this idea of the scientific method is all about reproducing things. Scientific method is all about teaching. That's even carried over into the idea of intellectual property. And it's really a problem to me, the idea of a code that people can't look found mistakes in GSAS by looking at the code. And we've had people point out mistakes that we've made by looking at the code. And that's, I think, absolutely essential.
Rebuttal, Bob?
I guess the thing I'd want to add is that having the code available for people to look at is, as Brian says, a check on our work, because people can then look at it and say, yes, this is right, no, that's not quite right, you need to do it this way. And there have been a few people who have actually looked at the code sufficiently to in fact point out errors, which we have promptly fixed after vetting them, and thank them all for providing that key bits of information. In fact, if someone finds spelling errors, I want to know about those, so we can fix the spelling errors that appear in the GUIs. Anyway, thank you all.